Hello everyone, this is Dr. Abdul Pasha. Today I am going to give presentation on power system operation and control. It contains a second topic, optimal operation of generators in thermal power stations. So earlier we have gone through the power system operation and control, basic terminologies, what are the basic constraints it contains. So every power system network may be idle or thermal. It will be associated with some basic constraints. So to meet the load requirement or load demand, we are going for some control operations inside the power system network. Coming to the introduction, here a good business practice is the one in which the production cost is minimized without sacrificing the quality. So in the earlier video, I told you that the quality of the power is important, very much important. The quality of the power involves voltage quality, current quality. So this is not any different in the power sector as well. So here the main aim to reduce the production cost while maintaining the voltage magnitude at respective buses. So operation of the economics can again be subdivided into two parts. One is a problem of economic dispatch, which deals with the determining the power output of each plant to meet the specified load. This we already discussed earlier. So such that overall fuel cost is going to be minimized. This is relevant to the economic operation of the power system network. Next, coming to the second case, the problem of optimal power flow, which will deals with minimum loss delivery, where in the power flow, it is optimized to minimize the loss coefficients in the system. So these two points are very much important to maintain the economic operations of the power system. By this, we can reduce the entire loss coefficients in the power system network. So economic dispatch is, however, determined in terms of fuel cost that will be taken per unit, so which will be generated and which does not include capital investment. So capital investment means whatever the entire expenditure we are going to be placed at the initial stage. So which will be also including maintenance, depreciations, startup and the shutdown costs. So everything is a cost inclusion. What is optimal generation of the generators? So coming to here, optimal operation of the generators include which corresponds to the equal incremental cost of all the generator cases. So here optimal operation includes all the generators, which may be from thermal side, which may be from idle side, whatever it may be the power generating case. So which will include equal incremental cost point of all the generators. So this may be treated at the respective bus. When you consider this optimal operation of the generators on each bus bar, the major components of the generator, their operating cost in the fuel input per hour, while maintenance contributes only a small extent. So fuel cost is meaningful in case of thermal and nuclear stations. As we know that availability of the coal and whatever the fuel requirement for the nuclear stations are more costlier compared to the hydel power stations. But what happens in the hydro stations, energy storage is apparently free. Even though it is free, but it cannot be available at all the instance. All the time we cannot expect the availability of the water. storage. So operating cost as much such that it should not be a meaningful. Next, coming to this optimal operation of generations, it is involved in the consideration of economy of the operation and also system security, which will releases of water at hydro generations. So what is the main aim here is to, in economy of operation problem, it is to minimize the total cost of generating real power, which will be taken place at various stations while satisfying the loads and losses in the transmission links. So economy of operation not only involved in the economic dispatch problem, but also it influences entire system. The economic aspect will influence entire system. So there is a reason to consider this economic dispatch problem. So here for simplicity, we will consider the presence of thermal plants only in the beginning. Why? Because here we may treat a continuous input case. But as in the case of idle in nature, the availability of the input may varies. It should goes to high and it should be minimal case. So the continuity of the input can be maintained by this thermal power plants itself. Next. So coming to here, whatever the economic dispatch problem we considered is really the solution of large number of load flow problems. So cost of generation is not fixed for a particular load demand, but it depends upon the operating constraints. So operating constraints here means we will take the limits of the given sources. So therefore, here are some of the constraints we will consider before taking the economic dispatch problem. We will define some system constraints. Based on that constraints, the economic dispatch problem is going to be designed. So what are the system constraints? The system constraints are basically of two types. One is equality constraints, another one is inequality constraints. What are equality and inequality constraints? That we will see now. Coming to equality constraints. So here equality constraints are defined in terms of its real and reactive powers and complex term terminologies, which will be derived from basic load flow equations. So here equality constraints are the basic load flow equations we will suppose to fix at a respective bus. If you write the corresponding expression, that is in terms of real power and reactive power, the term becomes P suffix P minus JQP, which is the entire power in terms of complex in nature, VIP. This is supposed to be fixed at each bus. When you consider the similar case of the current from this, then we may obtain the condition from the summation of Q equals to 1 to N YPQ VQ, where Y is called admittance. So Y is here admittance. When you continues to flow for the same expression here, PP minus JQP, then if you write this VQ to outside here in terms of its conjugate, then this becomes summation of Q equals to 1 to N YPQ VQ. So here this is in terms of P, this is in terms of Q. That means real and reactive power coefficients. Now make it as equation 1. Now we will assume some constraints here. The voltage Vp is EP plus JFP, which is complex in nature. Similarly, reactive term coefficient VQ as EQ plus JFQ. Then your admittance Y becomes YPQ equals to GPQ minus JBPQ. So these are the constraints which will be considered as in the manner of admittance, real and reactive in nature. Now substitute all the values whatever we defined like a constraints VP, VQ, YPQ, all these we need to substitute in the expression 1 here. Then we may obtain the rewriting expression. So on LHS side it will be same PP minus JQP, and instead of this VP conjugate you need to substitute this value. This becomes EP plus JFP. Here conjugate coefficient is there for here, then you need to place conjugate. After that this will be followed summation NQ equals to 1 GPQ minus JBPQ, which will be multiplied with EQ plus JFQ, where this coefficient will denotes the YPQ. So we have YPQ is GPQ minus JBPQ. And coming to here, this coefficient will defines VQ coefficient, reactive term coefficient. So likewise, if you extend this analysis again, PP minus JQP, QP, so which is equals to EP minus JFP. Here this positive sign will be changed due to this one of the conjugate term. This complexity will change as positive to negative sign. And summation Q equals to 1 to N GPQ minus JBPQ will be follows. Here the same expressions will be follows. Why? Because there will not be any conjugate term on the power. Now what happens means next we have to separate all real and imaginary coefficients. In this expression we need to separate all real and imaginary coefficients. Then the real term coefficient is P suffix P, which is equals to summation of Q equals to 1 to N EP into EP GPQ plus FQ BPQ. This is the real term coefficient, and which will be added to FP of FQ GPQ minus EQ BPQ. So this entire equation is called as real term coefficient. Now coming to reactive term coefficient, this is defined as QP, which is Q equals to 1 to N FP in terms of EQ GPQ plus FQ BPQ minus EP of FP GPQ minus EQ BPQ. So we are going to splitting this expression. We are going to splitting this expression for real power coefficient and reactive power coefficient. Then if you multiply these, then we are getting two parameters, real and reactive coefficients. So which will be applicable at the limits P equals to 1, 2, 3 up to so on N. So these are the equality constraints which will be defined from basic load flow solutions, which are the combinations of real and reactive power coefficients at respective buses. Now if you continue this procedure, here the defined variables are EP and FP are the real and imaginary components of the voltage, where EP is the real term, where FP is the imaginary term, which will be considered at the pth node. And GPQ and BPQ are the nodal conductances. Here G and B are called as nodal conductances. Nodal conductances. And susceptances. Susceptances. Where G is the nodal conductance, where B is the nodal susceptance. This will be derived from real and reactive power coefficients. Next, coming to inequality constraints. What are inequality constraints? The constraints which contains generator parameters, voltage parameters, transformer tap setting parameters, transmission line parameters, spare capacity constraints, security constraints. All these combinations may be defined as inequality constraints. So we may obtain inequality constraints from generator constraints, voltage constraints, transformer tap settings, transmission line constraints, running spare capacity constraints, security constraints. These will give you the resultant of inequality constraints. First, we will go with the generator constraints. What are generator constraints? Usually, you know that coming to generator case, we will generate power. So, this will be real and reactive in nature. Real power is treated for the useful work, and reactive power is treated for the production of field in the machine. So, we will take the combination as the square root term here. That is defined with kVA loading on a generator. So kVA loading on the generator is square root term of the PP square plus QP square, where PP is the real term power coefficient, where QP is the reactive power term coefficient. These are the variables for real and reactive term coefficients. And we should say that it should not exceed prescribed limits or values. So for this we will select one of the variables CP. That means whatever the real power term coefficient, reactive power term coefficient, when you remove the square root term, then we are writing PP square plus QP square, which will be much less than or equals to CP square coefficient. This will be denoting the prescribed value of the power coefficient, which is square root term, square term. So generator active power cannot be outside the range stated by the inequality. That we must consider. This is the generator active power coefficient PP. We should not exceed its range as stated by the inequality. So that's why we may say that PP minimum much less than or equals to PP maximum. So here PP is existing in between the limits PP minimum and PP max. So in between that, our real power term coefficient, that is PP, existing or lying in between minimal to max value. So it should be the meanwhile. Next, coming to here, while defining to the generator constraints, maximum active power generation of a source is limited again by thermal consideration and also minimum power generation. So this should be limited by flame instability of the boiler. That means adjusting the input side from the boiler section. So minimum power generation we can be limited or adjusted to the suitable extent by boiler flame instability. This is much more important. So if the power output of a generator for optimum operation of the system is less than the prescribed limit, that means P minimum, so the unit is not put on the bus bar. Why? Because it is not possible to generate that low value of power from that unit. That's why there should be a instability of the flame that must be considered from the boiler section. Similarly, the generator reactive power cannot be outside the range stated by the inequality. However, we say that this inequality should follow for a real power coefficient. Similar case, the generator reactive power coefficient also to be in such a way that it should obey the inequality constraint. But it is that QP minimum less than or equals to QP max. Your reactive power term coefficient QP also should be in the range of minimal to max. It should be existing in between minimal to max. However, we say that real power coefficient also PP should lie in between minimal to max PP. Likewise, your QP should exist in between minimal to max. So that means what it defines means the inequality constraints it should obey. Whatever it states, the conditions that it should be obeyed by this real and reactive power coefficients. So here, similarly, the maximum and minimum reactive power generation of sources are limited. Whatever the maximum and minimum reactive power that will be coming from the source, those are also to be limited here. So maximum reactive power is limited because of overheating of the rotor, and minimum is limited because of the stability limit of the machine. Now coming to the another constraint called voltage constraints. So it is essential that voltage magnitudes and phase angles at each node should vary with the prescribed limits or certain limits. So voltage magnitude should vary with certain limits because otherwise the most of the equipments connected to the system will not be operated properly. Or we may go for additional use of voltage regulating devices. This will impact additional cost on the power system network. When you are going for additional regulators into the system, which will make the system to be uneconomical. So that means cost of expenditure will be more. You are going to controlling the power. That means usage of regulators are more. For example, if you are using AVRs, automatic voltage regulators, the regulation of power is going to be takes place. This is one of the external burden to the power system network. You should bear this AVRs or whatever it may be, the regulators, controllers as your own. That will increases or enhances the capital cost of the power system network. So you should minimize these systems. When we go for this type of system means when the system response is lagging behind the output. That means you go for the regulators. So here it will be suitably defined with one of the expression called VP minimum less than or equals to VP max. The VP is existing in between minimal and maximum coefficients. This is the real power term coefficient. VP is the real power term coefficient. So here delta power angle will be considered in terms of delta P minimum to the delta P max. So every parameter, it may be real power term coefficient, reactive power term coefficient, or power angle coefficient, whatever it may be, they should be in the prescribed limits, which may existing from minimal to max. So these are treated as voltage magnitudes and phase angle magnitudes. We will treat these at respective bus or respective node P. Next, coming to this another constraint called transformer tap settings. Why should we go for tap settings? We know that transformer can change the level of voltage. So here we should go for tap settings. Tap settings, what they can do means they can adjust the levels of the voltage to the required extent. So we need to set the transformer tappings. So if an auto transformer is used, the minimum tap setting could be 0 and maximum is 1. We can set our required value with this variable. From 0 instant to so on, we can adjust our value. That means it is used to in the minimum tap setting 0 and the maximum is 1. Like that it can be treated. This will be happens for only one winding transformer. That means the limits are existing in between 0 to 1. 0 less than or equals to T less than or equals to 1. Similarly, for a two-winding transformer, if tappings are taken or provided on the secondary side, then it gives the resultants as 0 to n. 0 less than or equals to t less than or equals to n. What it means? The limits are existing up to n number, but here only 1. Why? Because the setting is possible from minimal is 0 and maximum is 1 by the auto transform. But for a two-winding transformer, the setting constraints are taken from 0 to n. What is n here? N is the ratio of the transformation. We are calling it by the name transformation ratio. Transformation ratio. So, phase shift limits of the phase shifting transformer can be treated in terms of the theta, where theta is the phase shift for the phase shifting transformer. It also should lie in between minimal to max. So, theta p should lie in between minimal to max. However, we considered every parameter starting from real power coefficient, reactive power coefficient, phase angle term coefficient. Likewise, here your phase shifting also existing in between the suitable limits, theta. Next constraint is called transmission line constraints. What are transmission line constraints? So, when power is generated, it is connected to the transmission network, then the operating power ranges in the transmission network are suitably defined with the transmission line constraints. So here in the transmission line, the flow of active and reactive power through the transmission line is limited by thermal capability of the circuit. So we can express this as in between Cp less than or equals to Cp max. What is this Cp max? Means maximum loading capability of the pth line. We have n number of lines. So here Cp max is the maximum loading capability of the pth line. Next constraint is called running spare capacity constraints. What are running spare capacity constraints? Means these are required to meet the forced outage of one of more the alternators case. So, if the system is involving with forced outages with more number of alternators on the system, then their capacity constraints are defined. This will also existing with unexpected loading on the system. So, the load cannot be fixed here. We may expect a variable load. So, this variable load also impact the running spare capacity constraints. Next, the total generation should be such that to meet the load requirement or demand, losses should be minimum. That means spare capacity should be available. That is G greater than or equals to PP plus PS naught. So what it defines this variables means here G is the total generation and the PSO parameter is called pre-specified power. Pre-specified power. So for to happen these such constraints, a well-planned system is one in which the space capacity PSO is minimal. Then only we can maintain the power system network in a well-planned, well-organized manner. Next constraint is called by the name security constraint. What is this security constraint? So, power system network security constraint and the power flows between the one of the buses are considered for the solution of optimization problem. This is one of the technique most useful in a power system network for dealing with security constraints. If the system is operating satisfactorily, there will be an outage that may be scheduled or forced, but some of the constraints are naturally violated. This is because, as we earlier mentioned, that consideration of each and every possible branch of an outage will not be suitably in proportion to the nature. That's why security constraints are considered mostly. So when there is a large system under a study, so network security is maintained such that computation is to be made with the outage of one branch at one time, and then computation of group of branches or units at another time will be considered. So time factor is one of the important factor here at respective outage of a respective bus. It may be P bus or it may be Q bus, like that. At each bus configuration, whatever it may be, ith bus configuration, we consider these parameters. Next, we will go with the characteristic curves. What are these characteristic curves? So, characteristic curves are defined with input and output characteristics. So, these will enable the performance of the power system network, how the power generation will meeting the load requirement, that can be suitably explained with the characteristic curves. Here we will define input and output characteristics. So what are these input and output characteristics? Means the idealized form of input output characteristic of a particular steam unit, that means thermal unit, is supposed to be considered for better explaining the characteristics that we will see in the next case. So what happens with this means it establishes the relationship between energy input to the turbine and output from the generator. So the relation existing for input and output characteristics are in between turbine and electrical generator. So input to the turbine is ordinate, maybe either in terms of the heat energy requirement or which is generally measured in BTU, British Thermal Unit, per hour. So here measurement is in terms of BTU per hour, BTU per hour, or it may be kilocalories per hour, kilocalories per hour. This is the one of the general measurement for the heat energy requirement. So as we generate the heat from the coal, from the combustion chamber, then the unit measured is a British Thermal Unit, or it may be kilocalories per hour. It is considered in terms of the total cost of the fuel, which is considered per hour in rupees, per hour in rupees, or rupees per hour. So output is normally the net electric power of that particular steam unit, and it may be collected in terms of kilowatt or megawatts. Whatever the output produced or generated is normally net electrical power, output power, which will be collected in terms of kilowatt or megawatts. That much range of power is generated as a output. So here in practice the curve may not be very smooth. Why? Because due to dissimilarities of the meeting the load requirement from practical data, such an idealized curve may be going to changes. That means it may be interpolated. That may goes to changes. So steam turbine generating unit that may contains minimum and maximum limits in the operation. So which depends upon the steam cycle, whichever used. Thermal characteristics are considered here, which is obtained from the materialistic in nature, and temperature ranges, whatever the operating temperature ranges, that may be considered. If you observe this figure, these characteristics will better explain the operating cost in rupees. The operating cost in rupees or fuel in million kilocalories per hour to the power output. Then the power output may vary slowly, which will be megawatts in minimal range from here to the power output megawatts in a maximum range. So minimal to maximum range is considered. So this curve we may goes to changes with respect to the fuel availability in kilocalories per hour. This will impact whatever the availability of the fuel to the power system network. Based on that, the power output in megawatts may vary slowly. So if the fuel consumption is less, the curve may falls. The curve may fall slowly. If the fuel consumption is within the prescribed limits, then your power output may goes constantly. So power output is constant when fuel consumption is availability of the fuel consumption is suitable in nature. Next curve is called cost curves. These are relevant to the economic operation of the power system network. We are defining the economic dispatch problem. So cost curves will define the economic dispatch problem. So these are obtained experimental. Cost curves are obtained experimental. How can we obtain this? Means to convert the input output curves into cost curves, fuel input per hour is multiplied with the cost of the fuel. Once again, to convert the input output curves into cost curves, fuel input per hour, how much amount of fuel you are giving or feeding per hourly basis, is going to be multiplied with the cost of the fuel. For example, fuel input per hour is calculated, then with the cost of the fuel in rupees is mentioned, then that product is considered. Straight away we may say that rupees per million in kilocalories. This product may be considered. That is kilocalories into 10 power 6 per hour is considered into rupees per million kilocalories. This expression better defines about the cost curves. As the fuel consumption is considered in kilocalories, we are getting the energy from that fuel. We are getting the energy in kilocalories. That will be calculated on hourly basis. Hourly basis we consider. So when you modify this expression, million kilocalories per hour into rupees into million kilocalories of the consumption is obtained. That is in rupees per hour. This is the resultant of cost curves. Likewise, we will calculate the energy consumption. Next case is incremental fuel cost curve. IFC curve. What is this incremental fuel cost curve? We already seen input output characteristics of the curves. So from that input output curves, incremental fuel cost, which we can be determined by utilizing the input output characteristics, we can suppose it to define incremental fuel cost. How can we define these? Means the incremental fuel cost curve is defined as the ratio of small changes in the input to the corresponding small changes in the output. The incremental fuel cost is a small changes in the input to the small changes in the output. When we express in a equation manner, incremental fuel cost equals to delta input to the delta output, where delta is the term which will express change. Delta will express change. So delta input to the delta output is delta F by delta Pg. So delta F is the input case, delta Pg is the output case. Here only delta represents a small change. Delta will represent only a small change. So these are the incremental fuel cost curves. So how they will represent means cost of the fuel in input rupees per hour to the minimal to the maximal power, which is output in megawatts. This entirely output in megawatts. How it going to be varies means based on the fuel cost. Based on the fuel cost in the input section, as it is in rupees per hour, then it may changes gradually from here to here. It will be slowly exponentially hikes. This is the exponential hiking nature of the output power in megawatts. This is the exponential hike in the megawatts. So here this limits may be splitted as delta Pg, delta F. What we defined earlier, delta Pg, delta F. So here delta Pg is the small changes in output. So here it is the fuel consumption, change in fuel consumption. When we go with the neighboring curve, cost of fuel in rupees per hour to the same output in megawatts, then we will represent with one of the angle called beta. This is also same as we suggested here, delta Pg, and this is also change in the delta fuel case, but we will express extra with the beta term coefficient for the exponential change of this incremental fuel cost. So what happens here means, as the delta quantities become progressively smaller, then it is seen that the incremental fuel cost is change in, that is input to the change in output, that is a D input to the D output. What it represents means change in input to the change in output, very smallest range. So here it is expressed in rupees per megawatt hour. It is expressed in rupees per megawatt hour. So here we will draw a typical plot of the incremental cost versus output power, which will be enabling that when the fuel consumption for the input section of the power system network is going to be increases, then output cost in megawatts, output cost in megawatts may also goes increases. So we need to go with the reduced initial investment of the power system network. So incremental fuel cost curve is obtained by considering change in the cost of generation to the change in the real power generation. This will be taken place at various points on the input-output curves. So there will be expectancy of every change of cost of generation, then it will be treated under real power coefficient and reactive power coefficient. So these are going to be happens under various input-output curves. When you consider the slope of the input for the same curve, input and output curve, whatever we shown here, when you treat the slope for this system, input output curve, then how can we represent this one means, see here, as the slope of the input output curve, that can be drawn in terms of IC of I, that is slope of the fuel cost curve, then it is represented in beta, that is tan beta, delta F by delta Pg in rupees per megawatt hour. So what it defines, there will be a small change in terms of the slope of the fuel cost curve. There will be expecting small change for every parameter. So incremental fuel cost of the ith thermal unit is going to be defined in every case for a given output power. As the limits of the ratio of the increased cost of the fuel input to the corresponding power output may increases in megawatts, then there will be increasing power output will also approaches to zero. So this we need to remind. For any ith thermal unit, for a given specified power output, what happens means ratio of increased cost of the fuel to the power output will increases and it may reaches to zero when there is imbalances in the power system network. So IFC is must considered. Why? Because it can only alone decides the economic problem of the power system network. It may be under loss, or it may be under gain, or it may be under balanced condition. These are the parameters can decide by this incremental fuel cost curves. That's why we are drawing these incremental fuel cost curves. By fitting a suitable degree polynomial, an analytical expression will be suitably fixed here as an operating cost that can be expressed as Ci of PGI. This is expressed in rupees per hour at the output of PGI. Here suffix I stands for the unit number. So generally it suffixes to fit a second degree of the polynomial, like 1 by 2 A PGI square plus BI PGI plus DI, which is expressed in rupees per hour. Then incremental fuel cost is DCI by DPGI. This is incremental cost with the variables A and B, which is called linear approximation. So here the unit number may goes on increases up to 1, 2, 3, 4, 5, 6, 7 up to so on n number. This is called unit number. So slope of the cost curve is called the incremental fuel cost. Slope of the cost curve is called incremental fuel cost and is expressed in units of rupees per megawatt hour and is expressed in rupees per megawatt hour. Likewise, we will express these incremental fuel costs. These cost curves will define the economic operations of the power system network. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.